Hi, and welcome back. Let's talk about the computational issues involved in implementing the sensor least absolute deviation estimator, or also, popularly known as the Powell estimator. So here's the objective. And before we talk about the computational issues, you can already see this is actually pretty easy to implement. It's just the sample average of the absolute differences between the observed variable y and then the maximum of xit beta and zero. Okay. And that's just one line of code here. First we take the average, we take the absolute value, and then we take the residuals from our model, which is my y minus the maximum of x beta and zero. Okay. So that's just this equation here. I'm going to need these two functions here, or the objective function only as a function of the parameters, but indexed by the data. And I'll do that both for the Powell estimator and for the Tolbit model. In this case, this Q Tolbit, well, that's negative of the sample average of the log likelihood contributions derived from the Tolbit model. So we looked at that last time, and I'm not going to talk more about how that actually looks. It's all inside this CREG collection of functions that goes with this workbook or notebook. Okay, so there's some computational issues involved in implementing this estimator because you need to find the argument that minimizes the sample objective function. You already kind of alluded to that you have some problems that this function is non-differentiable. So how do you do that if you're using a gradient-based solver? Okay, and the answer is you don't do that, at least not with this formulation of the objective function. You don't use a gradient-based solver because it's going to fail. It's going to require you to be able to differentiate the objective function, and this is non-differentiable, at least in these two types of kinks that appears in this objective function. I'm going to illustrate that in just a second with a little bit of Python code. Okay, so here one thing I want to highlight first is that as the number of observations increases, these discontinuities are smoothed out. And then also the problem with the kink due to these absolute deviations, it's not specific to the censoring that's going on in this central regression model. It's something that's common to any least absolute deviation estimator that you might use. And so the issues we also talked about, not that we couldn't use, you can't use the theorem 12.3 directly for inference, even though this is an M estimator. You can't do that for least absolute deviations either because it's non-differentiable. And then how do you get the variance covariance matrix, which is based on first and second order derivatives of the objective function. So that's kind of goes against the rules. But then there's other ways to get variance covariance matrices. It's still actually asymptotic normal. Then that's the first problem. Then another problem is that all predicted values, when all predicted values are zero, that is when xit beta is negative everywhere, you're going to get zero here, right? And then there's no variation essentially left in the explanatory variables that can explain why. It doesn't have to be so at the true parameters, but also at the trial parameters that you're trying, you may actually end up in the situation where the objective function is completely flat. Okay, and so that's a problem. Tolbit is not suffering from this at all. Even with like lots of censoring, you're not going to get these flat areas, and you're not going to get this the kinks in the objective function. It's going to be totally smooth, and you would have an easy time trying to maximize or the likelihood, okay, or minimize the objective function as a negative average of the log likelihood. Okay, so here's a little illustration. And so what am I doing here? Well, I'm taking a simple model here. So why don't we just take one with only two parameters. There's a constant. Okay, constant is 0, and then there is an explanatory variable which is uniformly distributed, so it's always positive between 0 and 1. And it has a coefficient 1. Okay, so we want to estimate this model, and then we have our residual variance. These are the true parameters. We want to be able to estimate these parameters using the CLAD estimator. Okay, we simulate some data with these parameters, and then we We don't need this guy. I'm going to talk about that later. Um, and and then what more do we do? Then we have the, you know, stack the, we have some starting value, which we just started this algorithm from 0, and then we might see if we can like minimize this objective functions that we had on the previous slide, the version that was only a function of the parameters, using either you know, the BFGS algorithm, or you could use like Newton. But the bottom line is this one here, it depends, it requires derivatives, depends on derivatives. Okay. Okay, so I have not specified what those are, so it's going to try to numerically differentiate this function, even though it's non-differentiable. Okay. And then we have Nelda-Mead, which is kind of, you know, simplex-based methods where, you know, it's an algorithm where you draw a bunch of triangles in the parameter space, and then you know, shrink and expand these. The bottom line is, you know, the Nelda-Mead algorithm is not relying on differentiating the function. It's just, you know, looking at triangles and, you know, making them smaller and bigger, and then eventually this algorithm is going to converge. Okay, so the bottom line is this does not depend on derivatives. Okay. Derivatives. So this is like what you will get, what you would use in a case like the CLAD estimator, where you have a like a non-differentiable objective function, and you have that many times. But actually this algorithm, you know, it takes a lot of iterations, and it's really, you know, searching around. It's not, you don't have the quadratic convergence as you would get with Newton. Okay, and BFGS is like a quasi-Newton algorithm where you're making an approximation to the Hessian through some sequential updating procedure. So this, you know, it would be best to use this on Newton if we could, but then turns out that could sometimes be a problem. Okay, before we you know, go back to the results here, let me just, you know, actually plot the objective function. So I'm plotting, there's a plotting tool for plotting functions here. And here's a function I want to plot, the CLAD, and then I want to I essentially want to plot it around an interval for an interval around betas. So here's my interval, you know, plus minus 5 for the true parameter I'm plotting, and then I'm plotting basically objective function with respect to parameter with index 1. Okay, so that's the slope coefficient. This is this one. So this, we go here between, you know, between -4 and 6, because, you know, here's the true value in the middle. Okay, so we're doing a little bit of plotting and adding a title, and this is what we get. So here, this guy here, that is the objective function for the Topit model. Okay, so, you know, the negative of the average of the log likelihood. It's nice and smooth. It has a well-defined minimum right at you know, close to the true value at least. And then you know, so an objective and standard optimization routine will have no problem finding this minimum. Now here is the objective function for CLAD. Okay, and you can see the first thing you see is it becomes very flat out here actually, and this is what I talked about before. Okay, so this is what happens if all the predicted values of y is suddenly getting centered, because then we have essentially that the objective function, if all these guys here are negative, so this returns 0, then you essentially just have, you know, the absolute values of y out there average over the entire sample. That does not depend on beta. And you can see, I mean, essentially here we can, why don't we, you know, change the interval, go a little bit further out, say, you know, maybe, you know, to -15 instead, and you can see it is really, you know, completely flat, right? So it is flat as you go out there. Now, what happens if you start your optimizer out here, you know, an accident, you don't know what the parameters are, right? Then your objective function, your optimizer is going to look at the gradients and say, that's pretty flat to me. I'm going to stop. And then if it checks if the second order derivatives are what they are, it's going to say, no, the Hessian is going to be singular. Actually, minimize is not telling us anything in this case. It's actually just saying, you know, optimization successfully completed in this case. Anyway, so this is what we have, right? And so now this was for a sample for 500 observations. Um, and actually, see, BFGS was actually getting decently close, and got the same result as as an Eldamide, but it gave us an error. It says that it cannot, the error is cannot be achieved due to precision loss, and this is because it's making finite differences, or trying to make approximations of those derivatives around kink points, and depending on where you are, those derivatives is going to change a lot, and how do you put those derivatives actually to zero when maybe there is actually not really a derivative that is equal to zero at the true parameters? Um, because it's this downward kink, and I think why don't we try to crank down the number of observations just a little bit further. You can really see here now the kinkiness of this objective function. Here is the minimum for the objective function for the CLAD observator. It's clear that there is a kink there, and if you try to calculate derivatives at this point, well, it's not going to put them equal to zero. Maybe it's going to say on the left hand side, well, it's not looking good. On the right hand side, it's positive, but you want to be somewhere in between, right? You want to be right at the kink. That's your solution. And so it may be when I increase the number of observations that you can't see those kinks, but they are really there. Okay. And so now suddenly the optimizer's ability to find the minimum, well, that could, for example, depend on what is the step size when you calculate finite differences to approximate derivatives. Okay, so this is a little bit disturbing. You know, I'm not going to comment here on what the estimates are, but um, it did actually look like Neldamide didn't catch it either. Probably it went somewhere out here. It found out it was flat, and there was no parameter change. So even though it potentially handles the problems with derivatives, it doesn't handle the problem that the objective function can't be flat. Okay, so that's a potential problem. If we were to say, okay, there is never any truncation point, so we just put this equal to 10, this parameter, so that it's never censored. You still have so now you're in a linear regression framework. You're trying to estimate with least absolute deviations. You can still see the kinks, right? And so how is the BFGS doing, trying to nail our estimator? Well, it's gonna it didn't really help us a lot, right? And so also Neldamide doesn't really have like a clear answer to what the problem is, because there's a kink right at the minimum. So how can it determine whether it's here or somewhere else where it needs to stop? So yeah, but then things get better once you have more observations, and so Neldamide should be able to really nail this this objective function and find the minimum here. It's probably here around here. It's 7.17. So it's doing a reasonable job. Still, BFGS is returning with this error that's just keep coming back, even though you look at the objective function and it looks actually quite smooth. The problem is that it really isn't. So that's some of the computational issues that are involved. You can even increase the number of observations here more, and you still get this error here. Okay, even though it's arriving at it's doing a reasonable job at arriving at some reasonable values, and this applies both in the case where you have censoring or where you don't, as in the current case, and so that's a help, right? It problem looks better. But look at what happens here. We still have this flat segment, and so if you were to start it out here, well, then you would probably get in trouble. So we could try to start the basically the object the starting values here, but say, why don't we try to subtract 10 to all of them, and then it's going to start in this flat area, and it's not going to get anywhere. So it's really important that you start the algorithm in a starting point where the function is not completely flat, and make sure, look at the predictions at the starting values. So everything is censored there. Well, you're not going to get anywhere. And so I think that's kind of what I wanted to say about this. So you essentially have all these problems that's kind of briefly written up here, you know. Yeah, so that's a problem. I didn't, you know, report the topic results, but I can tell you this is perfectly smooth. It's going to deliver the estimator in all places. Why don't I try one more thing? Why don't we just try to increase the amount of censoring? How would you do that? Well, you can just, you know, have a negative constant here. In this case, this would mean, since, you know, beta is this is negative, right? So you have you start at -0, and then x1, that's between 0 and 1, you multiply that by 1. This means that, you know, even if you look all those observations that are at the top, it means that everybody is going to be censored. Okay, so and then you can see, really, okay, now you have, at the true parameters, really, you have a flat objective function. So in this case, you completely lose identification with the censored least absolute deviation estimator. Whereas that's not the case for PROPIT, right? Because you assumed something about the distribution out there in the censored part of the distribution. And so if this is supposed to be normally distributed, well, then you cannot just have, you know, this parameter theta just grow and grow and grow, because then it's going to mess up with the probabilities of being censored, you know, implied by the PROPIT model. So, or you know, the PROPIT part of the probabilities are due to the normal distribution. Okay, so that's all. That's why we can, you know, we can even estimate TOPIT model if more than half of the sample is censored. Okay. Um, and let's try to see what happens if we put it, you know, to something less extreme, 0.5. I haven't calculated how much is censored here, but it looks like, you know, even in that case, well, I think on average with this data, exactly half of the observations is going to be censored. In that case, you know, the CLAD observation estimator also fails. And this is very intuitive, right? We're making assumptions about what is the conditional median of u given x. We say that is equal to 0, but if you never observe the median, you don't have any variation that can be, you don't have any variation, you don't have any constraints where this constraint, the conditional median is equal to 0, is binding, because it's always equal to 0, because all those or, you know, the conditional, and, you know, you basically never really observe what anything about what the median is, because you only have observations essentially above the median. Okay, so that's really that's a bummer. I'll put it back to the default values. And by the way, you can also move around with the, you know, the normality and so on, see if the and other parameters, and see if this is creating any the CLAD is able to estimate the model on the weaker alternatives, and we're going to look at that later. But this was just to focus mostly on the computational issues. So here, that was you know, that was all the problems, right? I mean, there is one solution, that is, you know, use an LDME and be careful. Okay, make sure you're not starting in starting values where all the observations are censored. Make sure you're not using the CLAD estimator for, you know, problems where half of the observations are at y equal to 0. Okay, because that would you can't use that estimator in that particular case. Okay, so here's a little trick. And so, I mean, this is not in the book. I want to tell you about the power of smoothing for dealing with non-differentiable problems. And so this is not because I think you should do this necessarily for the, I don't know, even know if this estimator exists. It probably does. But I just wanted to show how we can improve on the properties also in terms of the asymptotics and the and the computational issues by adding a little bit of smoothing. Okay, so what if in our model from before, what if we where is it here? What if we say, okay, this is not our model, but we added a little bit of artificial you know, logit error inside this. Okay, you know, one here and then plus one here and one here, and then if you do that and integrate that out, and you can scale that error arbitrarily down, then it's going to be a differentiable function, okay? Because then this integral here suddenly becomes, the integral over the logit form, or these logistic errors, you get them in closed form, and they're all smooth and nice, okay? Of course, it's going to be a different model, with a little bit of logit error here and there, but it has better computational properties. And then you can scale down that logit error as much as you like as you get more and more observations. Actually, that turns out to be quite helpful. So I tried to implement that. Okay, little just digress before we move on and talk about how to do that. Let's just do a few steps. Okay, so remember we talked about how the log sum was a little bit like the smooth max operator. Well, we have a max operator, right? So why don't we choose, instead of this hard max operator that is non-differentiable, just replace it by the log sum. Okay, and so this is nice because it's this parameter lambda, the smoothing parameter, the weight on the logistic error is, let's go to 0. This has the limit of approaching the max operator. So here's a log sum for two potentially random variables. Actually, one of ours is going to be 0. The other one is going to be x beta, right? But this is just a simple illustration. So if you take this formula here and take the limit and let lambda go to infinity, or sorry, not infinity, but to 0, well, then that error is going to disappear, and then you're left with the original max operator. But for finite lambda, just a little bit above 0, this function here, this is our log sum, right? That's a perfectly smooth function, right? Not when before you take the limit. This is just a bunch of sum of exponentials and smooth functions. Log is smooth, exponential is smooth, and so this is just completely smooth in changing sets, okay, or changing x beta, okay. So that's going to be helpful for us. Then there's the logit formula. Logit formula is still the same. Is still the same thing. Okay, so so here I call it capital lambda, and now normally you would be like a function of some variable, or utility index, or latent variable. That's what we call set here. Again, set that could, for example, be that could be x beta, or y minus max of x beta, or something like that. But bottom line is, let's look at the logit formula first. It looks like this, right? It's this is like the probability that set is positive, right? So you could also write the exponential of the exponential of set divided. Sorry, here this is a bug. Sorry about that. Need a division. There's all these things to keep track of, right? So you could have the exponential of set divided by lambda divided by 1 plus exponential of set divided by lambda, but that's going to be the same here, right? So just it's just a rewriting of that equation. So this is just the logit formula. And then we have scaled the standard Gumbel error, or standard logistic error with this scale factor lambda. Okay, and now you can see here, if you let lambda go to 0, right, this becomes this goes to negative infinity, right? So if set is positive, then this goes to negative infinity. What is the exponential of negative infinity? Well, that is 0, and then you got 1, right? And then you can also do it for basically a negative value. Then this becomes positive, so you got something that is going to infinity. So you got 1 over infinity, that's 0. So this is exactly just like what the indicator function would do. And the CDF of the standard normal, as you increase the variance, it becomes kind of wider and wider. As you make it smaller and smaller, they're going to get closer together, and it's going to, at the end, be exactly like the indicator function that just jump from 0 to 1, okay, whenever that variable inside becomes positive. Okay, so that's the limit for the logit formula. Then you can do something called I don't know if it has a name. It's called the logit sign operator. That's what we need, right? Because we need to calculate the absolute function. Okay, so what is that? Well, that is if this was an indicator function, you would have like 2 minus the indicator function minus 1. That would deliver the sign of set, right? Again, you get let lambda go to the infinity, this kind of Logit smooth sine operator that returns the sine of set. Okay, I can illustrate. I have a little Python code that illustrates in just a second. Okay, so then we have the smooth apps operator. Well, that's just the sine operator times the value, right? If you know the sine operator returns -1 if x is negative, right? So you know then you have -1 times set, right? You know, so that -1 that cancels the negative value, and you got a positive value. So now you got, you know, a positive value. And then if set is you know, positive to begin with, then the sine operator is going to return 1, and then you have 1 times set, but that's still set. You got the absolute value. Okay, and this guy here, well, that's converging to the original sine operator. So this is going to converge to the absolute value. This function here. Okay, if you just multiply by set. And this is just putting all this together. We can write out like our Logit smooth central least absolute deviation objective function, simply just by replacing the max operator by the smooth max operator and the absolute value by the smooth version of it. And if you let lambda go to 0, well, then it's going to converge to the original value function. But see, why are we doing all this stuff here? This is just because for a tiny little lambda, okay, just a little bit above 0, this function is actually differentiable. Okay, maybe if you have a very small sample, kinks are very big. Even in those kinks, it is actually differentiable. Okay, maybe you want to have a little bit more smoothing if if the objective function is very kinky, but you know, it is actually inherently differentiable for a positive value of lambda. So why don't we just look at that? And so in just a second, but before we do so, let me just show you the implementations of these, you know, of these different formulas. So you got the Logit formula here, BV, that's like my lambda, or you know, it's kind of a bandwidth. Okay. So it's like a little bit like a Logit kernel, and Jesper, he'll talk about, you know, non-parametric regression next time, and there'll be kernels in for kernel regression, and there'll be something called the bandwidth. So this is very much the same. Okay. So this is our Logit. This is the smooth apps operator, right? So that is basically smooth apps. Did I call it this? Yeah. This is returning 2 times that Logit formula -1 times whatever value I put in. Okay, so this is this guy here, right? This smooth apps operator, right? This guy here. Okay, and so then we have the smooth max. Well, that is just the log sum, right? So then we put all this together, and the only difference I made to before is before I would say max here, no, the absolute value, and here would be saying the smooth, or here it would say max, and here it would say apps. Okay, and now I just added these smooth functions instead. Okay, and so why don't we try them out? Okay, so here let's put a value in for like for set. So here set is a negative value, so we should expect that, you know, the Logit is going to return 0, okay, or something close to 0. And this is returning something that is, you know, also close to 0, because, you know, the max of a negative number, and 0, that's 0. And then you have the absolute value that's just going to return the absolute value, which would be close to 10. Okay, and this is what you see. If you turn it around and put it equal to 10, well, then you have the same deal going on, right? And so this is for a smoothing parameter of 1, right? But then you can change those smoothing parameters. Say I want to have it to say, you can see they're not exactly 10, right? They're close to 10 and close to you know, but not exactly. So but what happens if I put that smoothing parameter down? Well, they're going to be even closer to what, you know, the hard versions of these operators are implementing. Okay, so that's what's going to help us. So in the limit, as lambda go to 0, these operators is going to mimic exactly what we expect them to do with the hard operators. Okay, So this is very useful, not only in terms of estimating the sensor least absolute deviation estimator, but in many other contexts, like in discrete choice models, or in where you have tax systems that have kinks, like the tax system would change from bottom taxes to top taxes, right? Then there's a kink in the budget sets, and you may want to potentially smooth that out so that your model can be solved by adding just a little bit of smoothing that can sometimes help. Okay, so we end up here by putting all this together with the smooth CLAD estimator. I don't know if it exists, and I don't know exactly what the properties are. I know we're gonna get a little bit of bias, but at least here it is. Okay, so it's just an illustration. So here so instead of maximizing or minimizing the that's another error here. You need the argmin. So instead of minimizing the original objective function, we are just minimizing the smooth version of it. Now, this is nice because it's smooth and differentiable everywhere for lambda greater than 0. It introduces some bias, but that bias is going to disappear as lambda go to 0, right? Because then you revert to the original problem. When would you want to put those the lambda equal to 0? Well, that's when those kinks becomes kind of smaller. You don't need to smooth that much around those kinks. So and when does that happen? As n go to infinity. So as you have more and more observations, well, then you're going to put less and less smoothing on. Okay, in order for your asymptotics and your gradient based solver to work, you can put less and less smoothing on. That's exactly analogous to what we do with non-parametric estimation when Jesper is talking about kernel-based estimation. That is also lambda is going to 0 as n is increasing. Okay, and then you get consistency. You're going to get probably a different type of consistency. It's not root n consistent. That depends on how that lambda is, how fast that has to increase with n and so on. So I'm not going to go into this. Basically, you need to choose lambda, and a pragmatic choice here for this estimator is just choose as low enough that you can make it work. And then, of course, a more thorough analysis of how that would be chosen. If this were to be any estimator, well, that probably have to be taken care of. But I would say that's outside the curriculum here to figure out the optimal lambda. So here, what I'm doing is really just comparing the objective function of the hard CLAD estimator that uses the hard max operator and the hard absolute function, and then compared to the smooth counterpart. So what you see here, well, it's not hard. It's a little bit hard to see, but there's a kink, right? There's a kink right there. And actually, why don't we just try to put it, a little bit closer to see those, make those more visible. You see those kinks, right? But then what is a smooth one doing? It's kind of, watering out that kink by that Logit smoothing, right? So now this is much easier to find the minimum. The minimum here, it has actually a derivative of 0, right? And what is our estimator? How is that treating that? Well, right now things are not looking good with 5 observations. And by the way, this is a 2-dimensional problem. So even though it appears like it's having the minimum here, I'm just putting in the true value for the other parameters, so we don't really know where the minimum is. Actually, if we want to look at that, we should work with a problem where there's only one parameter. And actually, I'm not even sure that's probably not working here. I need probably at least 2. So anyway, don't worry about that. But just that's just to say this is a 1-dimensional picture. Okay. Anyway, so we need a little bit more observations. So let's do 500, and you can see now that really here's what is returned for when we're trying to minimize the smooth one. Well, what is going on? Well, it is actually well, this is close to 0.9. So it's not that bad. But it says it terminated successfully. It did actually get around the same estimate, but actually closer to the true value compared to the hard version that was not smooth. And no, it's also doing getting closer than nail the meat. But part of this is potentially due to bias. And of course, why don't we try to increase the number of observations a little bit, so the nail the meat is going to perform better. These estimates are very, very similar, even though I added a little bit of smoothing. But that was with this smoothing parameter of 0.1. So lambda on the other side was that was 0.1. So this is introducing bias. So why don't we try to see if what have a look at that bias, okay, and see the objective function. You can see they become further apart now because I've over smoothed. I've added a little too much bias. It's still very well behaved in terms of its differentiability, but the minimum of this function is going to be different from the minimum of the function of interest. Okay, so we get smoothing bias, and you can also see here now the parameters are very different from what we found with Neldomi. Okay, but nobody says we need a smoothing parameter of 1 to make this work. Well, we worked with 0.1 before, and that was working beautifully and did not result in a lot of bias. And we could potentially even try to put it even further down. And now you start to see these two functions here, these two approaches are getting very close. And so why why wouldn't you just use Nelda-Mead? Well, Nelda-Mead is in a very ineffective algorithm. It's a very robust algorithm, but it's not assuring quadratic convergence. Once you have a differentiable object, well, you can use Newton. Okay, so that's really cool, right? And so I know it's not really nailing the true parameter in this case, but that's because we work with finite number of observations. So if we increase it to like 50,000 instead, well, then of course you get closer. Okay, and I know I'm only doing one simulation, so you got variance in this. Okay, and each of them are performing reasonable well. Okay, so yeah, so that's kind of what you can gain with adding a little bit of smoothing on the objective function, make it more well behaved, but not add too much, because that would probably introduce too much bias. So and here yeah, so here with 50,000 observations, well, maybe you don't actually need that much smoothing. It's so you could probably do like a very, very small smoothing parameter. And here you can see actually BFGS didn't actually like it, but the smooth one actually did come up with a result nicely. Okay, so that's a lot of stuff you can learn. You can use smoothing for, make sure problems more well behaved, and that's good to know. Okay, so and let's start with the original illustration where you could see how these two functions become a little bit different, and it's kind of smooth wavers it out, right? So that's the idea, okay, of smoothing. Okay, so how do you obtain it then without smoothing? Okay, I mean, we talked about Nelda-Mead, and that's certainly a way out. I think what people do in this literature is was originally at least either to use non-gradient based solver or to use another algorithm. And then there's Powell. He had this other estimator that was based on a iterative linear programming algorithm. Okay, I'm just going to show you here, and it's not so much. This is not so much because I think it's utterly important for you to really be able to nail all sensor regression models. This is just to show that there's so many different approaches to solve the same problem, and you have to be careful in which one to pick. And so Powell found another way to solve this problem, use something called the iterative linear programming or linear programming algorithm, or ILPA in short. Okay, so here's the steps. What you would do is you'd solve a median, or start estimating a median regression for the full sample. That is, just regress y on x beta. Okay, but with median regression, so it's like estimated with least absolute deviations. Then you delete all the observations that are censored. Okay, and then you run it again on the censored sample, where the model is where the model with what observations that are centered is predicted by the model. So that is when the predicted values are resulting in censoring. And now, if you do this again and again, then at the end, if there is a solution, you have a fixed point where basically the model at the parameters beta you've estimated is implying that basically y is equal to the max of 0 and x beta because you're uh, because this algorithm has converged, and that's what he's proving. It shows that if its convergent process is converging, then at the local minimum you would have implemented this CLAD observation, um, CLAD estimator. That is, I mean, this algorithm, if it converges to a minimum of this not the smooth one, of course, but of this objective function here. Okay. So, and you can, I mean, this is just a another that's Python illustration of how you do that algorithm. You know, you start here, up here with doing a median regression where I'm doing that. That's what I'm doing here, least absolute deviations on the original sample. Okay. Then I store those parameters B here, and then I make a loop. Okay, you know, I loop until this stuff converges. I save what is the original values. Then I make some predictions, and then if the model is predicting based on the estimated the current value of this estimated parameters, predicting that the dependent variable is censored, well, then I run another quantile regression or least absolute deviation estimator on that censored data. Okay, then I collect the results again, and then if all those estimates that I got doing that is the same as the one I previously had, well, then it was because I was making exactly the same censoring in the last iteration, and you reached a fixed point. That's where Powell proved that this would be at the minimum of the original objective function. Okay, so this is iterative routine to basically solve this problem, and it's just a bunch of lines of coding, you know. So that's an idea, and then you can try it out here. I have to say here these standard errors that we're plotting here, they're not valid. Okay, these are just the standard errors that you get from the last iteration of this ILPA algorithm for when you're doing absolutely least squares. So I'm going to talk next about how to actually estimate those standard errors, because we can't use theorem 12.3. And so what is going on here? Well, you see our estimates, our true value of parameters is supposed to be 1 and 2. We have not a lot of censoring, only 5% of the sample, but yeah, we were able with this to estimate the parameters fairly close. Okay, so you know, maybe we want to add a little bit more censoring. How do I do that in this model? Well, I reduce the constant. Well, that makes all the x betas, you know, smaller and closer to the truncation point. So I reduce that. You see there's more censoring, and yet it's still actually being able to estimate the coefficient that's going to be 2 and 0.5. Okay, so ILPA seems to be working, and actually it also turns out to work, and that's a property of Powell estimator if you have heteroscedasticity. And so why don't we try to have add some heteroscedasticity? We did that before, right? See if it can still nail it. Well, it didn't matter. We have this heteroscedasticity by this additional parameter delta that was controlling the dependence on the variance on x. That even with that, that would totally kill Topit, but it's not killing the Powell estimator. Okay, I'm going to put that back to original values, and then move on and talk about how to bootstrap standard errors, because we can't really use these standard errors that's coming from the estimation output. So we need to do that. And bootstrapping, that's a simulation routine where you basically use the sample to generate a distribution of estimates. I'm going to talk about that in just a minute.